good morning, good afternoon, good evening, wherever you are. My name is Eric Nijveld, co-founder of technologycatalog.com. And for those of you that are not yet familiar with the platform, I would encourage you to have a look. The platform contains hundreds of technologies to improve business performance. And the title of today's webinar is Production Forecasting Made Simple, Fast and Robust. It will be delivered by Peter Cunningham, Director of Serafim. The webinar will last about 30 minutes. If you have any questions, please type them in the Q&A box on the left-hand side. The webinar will be recorded and you will receive a link after the webinar, and feel free to share the link with your colleagues. And I would now like to hand over to Peter. Peter, over to you.
Hello, everybody. As Eric said, my name's Peter Cunningham. I've been working on what I'm going to tell you about, the Serafim Future production forecasting software. I've been working on it for about 20 years with my colleagues. But let me start the presentation. So if I can share my screen. So what is the problem that Future addresses? Well, let's start from the basics. Oil and gas fields generally take a long time to be produced, 40 or more years. And that means that the value of anything that you do, drilling the original wells, putting in everything, and all the work that you do in the course of the thing, depends not only on the volumes of oil and gas that you produce, but when you produce them. Because, a barrel of oil in 20 years' time is less valuable in NPV terms than a barrel of oil in a year's time. So that means, as far as possible, you want to have accurate forecasts. Now, as everyone amongst you who are from a subsurface background, an oil and gas subsurface background, what drives the forecast is multiple things. The production from an oil field. It's ultimately the geology of the subsurface where the oil is a very important factor. And then the process of getting the reservoir to flow. Are you depleting? Are you injecting water, and so on? The very significant pressure change required to get the oil and gas from the subsurface, sort of 3,000 meters down to the surface, and then going on the pressures in pipelines, and then finally the limits and capabilities and limits of the processing facilities and the separation and so on. Now, all these factors are handled generally by separate experts, geologists, reservoir engineers, facilities engineers, and so on. And you need to put them all together to get an accurate forecast. Now, that's something that's handled, existing industry standard software handles that well, whether it's in the form, in its very simplest case, it's reservoir simulation with representations of the surface network, or more commonly, what's called an integrated asset model, which precisely describes in approximately all these elements. Where the problem arises is that these industry standard integrated asset models generally prove to be too slow for the big complex networks that you encounter. Oil and gas fields are not usually found in isolation. So you've normally got, maybe 40, maybe 100, maybe 200 fields in close proximity. And it's always worthwhile, it's generally worthwhile to try to save money by sharing existing facilities as you discover new fields. And that tends to lead to complex networks. And so the problem that the software has is a bit like, if consider Microsoft Word. That would be fine for its editing a report of, say, 20 pages. But the software would start to have problems if you tried to edit a book of 400 pages all in one go. And it certainly would have problems if you tried to edit an entire library of books, hundreds of books, all in one go. The software wasn't fundamentally designed for that, and so it runs into problems of slowness. And that's essentially the problem that arises with complex networks. They have become too big, and yet an accurate forecast could well depend on the whole system. If you've got a constraint at the top, you bring your new wells, you start producing your new wells, but in order to allow them to flow through the facilities, you might have to shut in existing wells, and the cost of that depends on choosing the worst available wells, so that you lose the least production. Now, the ideal is that, for practical reasons, you in the ideal world, you'd be able to have software that can handle this. And for something, this diagram shows part of the Brunei Shell production network. As I say, it's only about a third of the total, but each of those colored squares at the top represents a platform, and the smaller boxes indicate the key processing equipment within it. And so that's something of the order of 300 wells and 100 and so key nodes in that production network. And so that's something that's beyond the limits of the industry standard integrated asset model software and algorithms from the 90s. So the ideal is that you want to be able to quickly to give a forecast for the standard things that you do to your complex assets, drilling of new wells, the debottlenecking of facilities. So if you've got a constraint, and if your facilities are limited, it's usually worthwhile to find out whether it pays to replace your separator with an upgraded one. On the practical side, in day-to-day and month-to-month operations, you want to know how much production you're going to be losing when you shut down certain platforms for maintenance and so on. If your pipelines are subject to a number of constraints, including velocity limits, and those are the sort of things that if you find that the pipeline is suffering from corrosion, these might change, and you might need to update all your forecasts rapidly to reflect that. And then finally, there's all the myriad events that happen in operations, and you want to be able to have a grip of that and to forecast what's going to be happening over the next month. In the medium term, of course, you want the sort of 5-year time frame, you want to have your forecasts for your business plan, and in the longer term, you want to have them for reserves. So in an ideal world, you'd want all these different forecasting tasks to be executable with a press of the button. But the problem doesn't limit that in the sense that you not only want that, but you want a wide variety of information from your ideal large asset production forecasting system. You want to have the wellhead profiles, what the wells individually produce. But then going on, you need to be able to say how much do you actually sell once you've taken off the amount of gas that needs to be flared and used for power and so on. you want, when you're considering a new project, say drilling of new wells, you want also to know what the incremental sales are. So your new wells may bring you 4 million barrels, but if they cause the loss of 500,000 barrels from existing wells, because these wells have to be shut in, that's an important factor to be included in the economics calculations. On the operational side, you want to keep track for all the various operations that are going on. You'd like to know what the impact of them are. You may also, for planning, you want to have an idea of, what are the potentials of the various parts of the system. What could the wells produce if we weren't subject to the facility constraints and so on. And of course, in the operations side, you want to handle all the complexities of downtime and so on. So that is the ideal, and we believe that, and Future is designed, and we believe does deliver more or less that, even for the largest assets that can be found currently. The Future took the approach of trying to keep everything as simple as possible, so rather than aiming to deliver a platform where you could conveniently model all the physics at any one time, it aims instead to give you a platform where you can model only the minimum level of physics that you require to describe your problem. So in other words, it gives you the platform for simplification as much as possible. And the idea there is so that it goes as fast as possible and can cope with, as big as possible systems. So we started with the question, what's the minimum required for a realistic forecast? Or another way of putting it, what would, if it was not the case, would you say that the forecast was simply wrong? So the first one is that any realistic forecast needs to be reasonable in terms of what the wells can deliver. If your wells can only be capable of producing 10,000 barrels a day, then if you forecast 15,000, it's simply wrong. Similarly, it wants to be realistic in terms of what the facility and pipelines can handle. And finally, it needs to have a realistic choice of the prioritization that I was talking about earlier, of the appropriate choice of wells to flow, because this is something, it makes a big difference whether you're flowing a new well with producing only 2% water, or you're producing old wells which are 98% water and only 2% oil. When you add these up all together, that minimum requirement is basically, we're back to what we were talking about at the beginning, the integrated asset model calculations. That's, in some ways, that's a minimum that's required. How then is it the case? Well, as we said, the traditional algorithms run into the practical problem that they take too long to run on big assets. It could be multiple hours, or in the very big assets, it could be multiple days, which is not very much use if you need an immediate answer. So moving on to in terms of from the point of view of what a software system has to deliver. The key thing is to being able to carry out these calculations quickly and robustly, and to have all the range of further features required for a practical system. We believe that Future has managed to solve this problem, and as such, it's what we might describe as a general purpose asset, the world's first general purpose asset model. In other words, an integrated asset model that is fast and robust enough for the full range of forecasting tasks. And the key to it is a new network solver algorithm that's described in the SPE paper 200754. And by using a new mathematical algorithm to solve the network flows, the software can run in an example based on the BSP part of the BSP network that we looked at. It ran 1,000 times faster than existing network solver algorithms, and that, we believe, enables Future to achieve what we talked about earlier in terms of, what is the ideal. It's been in continuous development for the last 20 years or so, and it's throughout that it's been in use by all companies, and we've got a lot of testimonials and so on from them. The main customers at the moment are Brunei Shell, they've got the most complex Future network with full pressures and everything else. ADNOC are starting. Various the parts of Total that Total took over from Maersk are users, and another big user is the North Oil Corporation in Qatar, and then there are a variety of other users. I'll just finish off with a bit of background about us, and then I'll move on to the demonstration. So Serafim was founded in 2000, and we're based in Belfast. Our focus was not so much software development, but more consultancy, with a aim to specialize with a focus on the more mathematical aspects of reservoir engineering. But we fairly soon got asked by one of our early customers, Adex Petroleum, to provide them with some software, and that led to the birth of Future. So it started in 2003 with an initial focus on facility constraints. Another major step was when the then Maersk Oil got us to start using Future to help to set them up to use Future on the Al Shaheen field in Qatar. And then the final key step in terms of the development of the software was with Brunei Shell, was the completion of the pressure calculations in about 2016. And throughout that, the development has very much been steered throughout by the customers. Okay, so to finish off, I'm going to give you a quick demonstration on a 250 well demo model. Okay. Eric, are there any questions or any raised hands or anything at the moment?
No raised hands, so the questions we'll handle at the end.
Okay.
Yeah.
All right. So this represents a system with here. This is the list of the wells. In a variety of pads flowing to separators, and then with constraints on the gas and water systems. So we've futures set up to generate not just a single forecast, but the whole spectrum of forecasts. So here it's set up with about 12 forecasts, 8 of them being various options. The NFA is the no further activity, so it's existing wells, and then looking at a forecast with additional wells, and then with a new project, and so on. And then there's also a range of forecasts using both deterministic calculations and probabilistic calculations on the low and high side. So future, when it calculates, it generates forecasts, all the list of required calculations that we talked about earlier in the ideal world. So the wellhead rates and the incremental sales forecasts for not only the wells, but also all the projects, all the nodes, all the reservoirs, etc. So what that looks like here, this is the historical oil production, and then here are the range of different forecasts. Now, that number actually becomes it's reasonably easy for an experienced user to navigate and make sense of it. But for demonstration purposes, I'm going to restrict it to 3 forecasts, and then what we're going to do is run the forecast. You can see the sort of speed and performance, and then we'll run it with an additional constraint. You can see how practical it is to compare results and so on. So take the original list, and we'll restrict ourselves to the existing wells plus the infill wells, and then the existing wells, infill, and this project X. So this is with monthly time steps for those forecasts. They're all being run in parallel. And here you'll see we've got the 3 different forecasts with the effects of the constraints on the gas gathering and the water disposal. So if you look here, you'll see this is the constraint on the gas. So let's rerun those with an additional constraint. So here perhaps we'll put a limit on the gas handling of the B110 compressor. So this is currently, so let's put it at 30 million. So we'll put an additional gas constraint, and then rerun. And so if we compare now this is a comparison of the forecasts with the constraint and the prior forecasts, 3 forecasts without it. So here, if we we'll see the effect and so on. And when we go back to the original one, we can again make the comparison. We'll see the extent to which the system has compensated for that by, given that there's an existing gas constraint, it can simply swap oil gas production from here. It can bring further gas production there, and so that moderates the effects. So that's a quick demonstration of the calculations. And as I say, our estimates are that in with the more traditional integrated asset model calculations, those calculations would be taking at least 1,000 times faster. So instead of the 10 seconds, it would be 10,000 seconds, i.e. sort of 2.5 hours. Okay, well, thank you very much for your attention. I pass it back to you, Eric, for questions and so on.
Yeah, thanks, Peter. And we can take a couple of questions. And hey, first of all, great to hear that ADNOC is now one of your customers. It's something I didn't realize yet, so great to hear. Mm-hmm. And if anyone in the audience has a question, you can type it in the Q&A box on the left-hand side. Hey, Peter, to start with one question. So like the demo you gave and this setting up this model based on a 250 well development. So how long does it take to set up such a model roughly for an experienced user?
About if the historical data is available, in a spreadsheet or in a database, and the lists of wells is available in Excel and so on, probably about half an hour.
Okay, so that's very quick.
Yes, it's one of the features of the development. As I said, it's been developed over the course of 20 years, and one of the things that we've done throughout that is, it's been driven by customer requests, and one of the things they often do is, if something takes a long time, they've asked us to automate it. So there's a variety of tools to speed things up. A lot of it's oriented. If you've got the information in a simple tabulation in Excel, Future can read that and set up the model accordingly.
Okay, excellent. Hey, and what type of support do you provide, and how do you provide it? Is it mostly remotely or is it on site?
We provide a mixture. I mean, we're very keen to visit our customers, because particularly when it comes to refinements and sort of making sure that it meets their requirements. But day to day, most of it is handled remotely. One of the key aspects of our support is that the software is deployed and updated via the web. And our system for dealing with issues that arise is to fix them immediately and put out any updates required, usually within 24 hours. And the idea then is that the key thing there is that if there is a problem, only one person encounters it and then it's fixed. The rest, pick up the update, and that minimizes. We are quite a small company. That minimizes that gives us more time to do other things rather than dealing with 10 different people encountering the same issue. So it's a big part of our support is immediate updates as required.
Excellent. Hey, and is it possible to start with a trial or perhaps even a free trial?
Yes, and you can download the software, and there's a free license and available for, but it's limited to models with 25 or fewer wells. And so you can use that for your trial. Alternatively, if you want to trial it with a bigger thing, just contact us and we'll give a time-limited trial license.
Yeah, excellent. And I suggest when we share the recording with all the about 150 people that registered for this webinar, that's also something that we can highlight to them.
Okay.
And there's one question, perhaps linked to the previous one. Is the data source available for public? Did you use time series for prediction?
Sorry, I don't quite understand.
I'm also not 100% sure. And Mustafa, if you can type in perhaps a few more words to clarify the question a bit further. So the question was, is the data source available for public? And did you use time series for prediction?
It's an important part of the forecasting for existing wells will often be decline analysis based on, yes, the time series of of allocated historical production or well test data, and Future loads that data and then gives you options for either automatic or manual decline curve fitting with a full range of options, exponential, harmonic, and hyperbolic, and so on. So yes, it works. It works with the importing of the historical and well test time series. It also works with the other wells, new wells. You may want to describe them with externally generated forecasts, for example, from simulators, and those again are imported as time series. In terms of the openness of the software, the code is not open source, but the algorithms are. We do put the algorithms in the public domain. So, and we would be prepared to open the source code to inspection by the customers as required.
Yeah, thanks. And I think, and I saw a couple of other follow-up clarifications posted by Mustafa, but I think that answers it. And also you refer to an SPE paper, the paper 200754.
Yeah.
And that is, of course, also available to everyone.
Mm-hmm.
There are no further questions, and it's indeed, we indeed took a little bit more than half an hour. So with that, I suggest we close the webinar. If any one of you has any further questions, of course, please reach out to Pete directly. The recording will be shared with everyone, those that attended today, as well as those that registered and will hopefully have a chance to view the recording at a later stage. So thank you very much. And with this, we close today's webinar and looking forward to seeing you next time. Many thanks, Peter, for presenting.
Well, many thanks for the opportunity.
And have a great day, everyone. A great rest of the day.
Okay.
Bye for now.
Okay. Goodbye and thank you.
The paper 200754.
Yeah.
And that is, of course, also available to everyone.
Mm-hmm.
There are no further questions, and it's indeed, we indeed took a little bit more than half an hour. So with that, I suggest we close the webinar. If any one of you has any further questions, of course, please reach out to Pete directly. The recording will be shared with everyone, those that attended today, as well as those that registered and will hopefully have a chance to view the recording at a later stage. So thank you very much. And with this, we close today's webinar and looking forward to seeing you next time. Many thanks, Peter, for presenting.
Well, many thanks for the opportunity.
And have a great day, everyone. A great rest of the day.